get started. For the midterm exams, we're a little more mixed this time than last time, but many of these did quite well. Maybe the first two problems were maybe the most problematic, and we should talk about them a little bit. First one, remember, was considering the limit where the speed of light is infinite, which means essentially that all changes of charges or currents have their effects immediately everywhere in the universe, essentially. So that means all information travels immediately at any point in the universe. So in that case, first then V becomes negligible compared to this very large C. So that means U essentially becomes C our unit vector. R dot U becomes then just CR, right? So here, what we have is then R over CR cubed. So that is 1 over C cubed R squared, right? And of course, in the C squared minus V squared, so somebody from IT is apparently on their way, but there's only one person, everybody else is sick or on holiday or whatever, and they're still busy at some other building. So hopefully by a coffee break or so they'll be here at least the second half. We can do without beeping. Then, of course, C squared minus V squared just becomes C squared here. So this term is C squared times CR unit vector, so this is C cubed R unit vector. Well, and this, there's only one C here, so this goes proportional just to our C A or so just one power of C. Right? So that means with this term together, this just becomes our unit vector over R squared, and this becomes something that goes as A over C squared times R, right? But now, in the limit C to infinity, anything that drops as 1 over C squared drops out. So this term drops away. So what's left over is just this term here. So what we're left with is Q over 4 pi epsilon naught R unit vector over R squared. And that, of course, should look very familiar, right? That is simply the electrostatic field from a static point charge. So that's kind of what you expect if the speed of light is infinite, everything is transmitted immediately. No, we don't have the beeping anymore. Yes, not the bottom of the beeping. Very nice. Can you still hear me? Kind of? Yeah. Right. I guess the recording won't be greatly dead. Nice. Okay, so everything is transmitted instantaneously, then technically you always just have a static situation, and so the field essentially becomes a static point charge. So for the, this makes sense? Any questions on that one? Okay, if not, then we can go to the second point of the button here. And if there's more questions, I'm pretty sure Thursday in the tutorial would still be Hassan, might explain more about it. So then we had our situation here, something on the z-axis. We are calculating radiation here. We have something going with some radius r, some velocity v that should be much less than c, around the circle, and here's some angle theta, and we're located right here. Thank you. Is there a code that I should know how to do that?
I don't know why it's doing it. Let's see.
So let's start on this one here. First of all, if we have this limit, then again our u vector is simply just CR unit vector. That was the limit that we should take then. What makes radiation, of course, is only this term. Everybody remembers that. So we have to figure out what is u cross A. In what direction is the acceleration pointing here? So this is our vector, our unit vector here. If we're going around a circle, in what direction is the acceleration? In what direction is the acceleration vector pointing? What's the center of the ring, right? So the acceleration goes in this direction here. That is our vector A. It's here, right? And what is the size of the acceleration A? That's of course v squared over r, or omega squared times r, right? Okay, then what is the fact? The vector u cross A is, first of all, that was a little bit tricky. What is the angle between them? The angle between them is this angle here, right? Let's call that chi. We have the right angle here. This is theta. So this is just 90 degrees minus theta, right? That's the angle between r and, so this is of course C r unit vector cross A. So this angle is this one. So this is C times A, or omega squared r, times sine of this angle chi. But what is the sine of pi minus theta? It's just cosine theta, right? So this is C omega squared r times cosine theta. And in what direction is that pointing? And this vector dots this vector points somewhere out of the plane. Right? So that goes in y direction. That's the phi direction that goes up. Okay. Then we need r cross u cross A is then r omega squared r cosine theta in the theta direction, right? So we have that in this direction cross this one has to go out in essentially this direction. That's the theta direction. Okay, that's this part here. And of course r, if we have some height z, and r is the square root z squared plus r squared. Right? Okay, then we just need to figure out still what is r u is, if u is just CR unit vector, because it's simply just CR. Right. Okay, so then we have the radiated electric field being q over 4 pi epsilon naught. Then let this out, r over c cubed r cubed. That's that one. This one drops off, and we're left with r squared squared r cosine theta in the theta direction. And we have this. Okay, and we can replace epsilon naught c squared as just, and did I? Sorry, I forgot a c here. Sorry about that. I forgot the c in here. partly. Then the magnetic field is cross 1 over C, our unit vector cross E. Our unit vector cross this one, R cross this, gets us back into the phi direction. Right? So that gives us just a vector 1 over C, so Q naught, Q U naught, omega squared R over 4 pi C cosine theta over R times phi unit vector. Okay, then we need the pointing vector here. I hope everybody remembers what the vector. Pointing vector S 1 over U naught plus B equals U naught over C Q squared over 16 pi squared cosine squared theta over R squared and the R direction times this pair of omega squared. I have the all terms there, I think so. Okay, so that's the pointing vector at any given time t. So now was another little trick. So the pointing vector at any point goes thus in this direction, right? This is S of t, and essentially that kind of goes around depending on where we are, right? So everything in xy direction will cancel out because you have components from everywhere around this ring. The only thing that's left over is the projection on the z-axis. So that means the time average is time average is simply just this at any given time times cosine theta, right? So, and that goes on this end. Because on average, everything is will cancel out because you get contributions from everywhere. That's one of the exact component that is left. So it's mu naught over C squared over 60. Well done. Thank you. Cosine cubed. So that would have been the complete solution to it. Does this all make sense? Any questions? Anything else we should discuss? So I think all other problems were relatively unproblematic. Maybe we can go back to the last one, and that then really brings us to the lecture, the Minkowski diagram. So the Minkowski diagram for the Lagrange-Barn paradox. We had discussed that briefly, but can't hurt to do it again. I think we'll do this some more. So, Minkowski diagrams. Minkowski diagrams were diagrams of time versus any space coordinate, let's say x, where you draw vectors, say x mu in terms of ct, x, y, z, or you can write this x0, x1, x2, x3, right? And you remember, so let's call this 4-vector x. And you remember that we had defined this Lorentz invariant 4-vector scalar product by, how did we do that? What was the definition of that? It's a generalization of just the scalar product of 3 vectors. You just have x squared plus y squared plus z squared. But including time, what was the main difference now? So was it x naught squared plus x1 squared plus x2 squared plus x3 squared? And was it that, or was there something missing? It's not that straightforward. There's a minus sign somewhere. There's a minus sign coming in.
I think it's at x0.
Exactly. The time component comes in with a minus sign. Right? And from that we have motivated that you can do all the Lorentz transformations, time contraction, Lorentz, time dilation, Lorentz contraction, with our typical Lorentz matrix. So say we are going in. That was everybody got that right. The fourth problem, say if you go in some direction E as E naught, say in the Z direction, or it's not X direction. So let's call this beta C X. Then we have this Lorentz transformation matrix of these 4 vectors as given by gamma minus beta gamma 0, 0, minus beta gamma, gamma 0, 0, 0, 1, 0, 0, 0, 0. Right? So everybody remembers that. And then also in our Minkowski diagrams, we could split up different regions, say from vectors going from the 0 point to any other point here. The diagram can essentially be divided through these light rays. So if we have x equals minus ct, and we have x, so no components in y and z, x equals ct, then of course along these lines, x dot x equals 0, right? Those were our right line, both lines. And then we have vectors that go up here with a larger component of t than x. X0 is larger than whatever you have in the space components. So here you'd have x dot x less than 0. And this also means that if you go along x as a function of time, you go slower than speed of light. So it's something you can physically do. So you can actually go in real time, go along such a trajectory. So this were time-like world lines. And here you actually cover more distance in space than in time. So if you wanted to go here, you would have to move faster than the speed of light. And that's physically not possible. So there is no way that anything, any information could travel from this point to this point in space-time. So this is really a space-like separation. Okay, maybe coming back now to this ladder and barn paradox. And so here we have t, that is the time in the frame of the barn, right? this is the x-axis in the frame of the barn. The barn has some length of, was it 10 meters? Right? So here's the back door and the front door of the barn. And we have our light race here again. Now we have a ladder that in its own frame is 20 meters long, but it is traveling at a large speed, say like this. If this is where the ladder is going, if you're in the frame of the ladder, that means you're not moving anywhere. So this actually is the time axis of the ladder, right? And the x-axis, so things that are simultaneous in the ladder, so we can say anything here is simultaneous in the barn frame. The x-axis of things that are simultaneous for the ladder is then also twisted like this. So this is x prime for the ladder. So now we have the ladder in its own frame being 20 meters long. But, so let's on here, the length of the ladder is then such that this actually is the 20 meter. If it's this ladder frame. So for the barn, but for the barn frame, the ladder is Lorentz contracted and has this length. So for the barn frame, the ladder goes through like this, Lorentz contracted, and with the speed, of course, less than the speed of light. So like this. This is again CTL. For the barn frame, the ladder goes through like this, and the time distributed like this way. Right? But in the ladder frame, the ladder actually has this length, and it moves essentially a long time like that. Right? So this is happening simultaneous, and you can see that it hits this point where essentially it hits the end of the barn. So the barn is now contracted to only 5 meters. But it hits this point at a much earlier time than it hits this point. So that, if everybody remembered the ultimate solution, that opening and closing the front and rear doors is not simultaneous in the ladder frame. So that means the rear door is open long enough to allow 15 meters of the ladder that it's longer than the barn to go through before the back door closes. Okay, that was that. Any other questions? So this was really just bringing us back to the topic of what we're really talking about today. Any other questions on the exam? Well, if you have more questions, as I said on Thursday in the tutorial, I'm pretty sure we can discuss more. All right, then, I think last time, that was, what's 3 weeks ago, I guess, we left off already with a definition of the velocity vector, right? Did we? I think so. But let's just maybe do this here. So, the fundamental statement of relativity now is that you have any vectors A and B of this form. The vector product A dot B, or we can write this as A mu B mu, or minus A naught B naught plus A1 plus 2 plus A3 B3. What was the most important statement about this 4-vector product? Why we started defining that in the first place? What if you evaluate this in one frame and compare the value of that in a frame that moves very fast? Does the value of this change? Right? That was the main reason. We saw the ways of the Lorentz transformations, and the Lorentz transformations are exactly designed in a way that they do this invariant. So this is invariant, means if you take two properly defined 4 vectors, do the scalar product between them, that will always be the same no matter in what reference frame you calculate. Okay, and you see that can essentially derive, say, most of special relativity simply starting out with proper 4 vectors and using the fact that this is invariant. Alright, so we had started trying to figure out velocity. Everybody knows velocity is dx over dt. And then the first attempt, I think we did that last time, was, say, if we derive a 4 velocity as the x4 vector over dt. Anybody remembers? Was that a good way to define this as a 4 vector? If it's defined well, what do we demand then? If it's properly defined as a 4 vector, in particular what we want is that eta dot eta is invariant, right? So it does not depend on any velocity. So this is invariant. But if we define eta like this, what this is, and the 0 component, d over dt, just gives us a c. And then we just have the regular velocity, the 3 velocity. So often I write 4 vectors also with a time component, and then the 3 space components, x, y, z, just as another 3 vector. That's just a faster way of writing it. So then, eta dot eta becomes minus c squared for the 0 component, right? Plus b squared, right? But is that invariant? Will that always be the same no matter what velocity boost you give your system? Certainly not, but because there's a velocity in here, you can calculate this in a frame in which you're moving along with whatever particle you're considering, then the velocity is 0. In some other frame, the velocity is not 0. But we know we can rewrite this as minus c squared, and then 1 minus b squared over c squared, right? Just pulling out minus c squared here. But this, remember the definition of the Lorentz vector, right? So this is minus c squared, 1 minus beta squared. And how is 1 minus beta squared related to the Lorentz vector? To gamma. Remember what the definition of the Lorentz vector was?
1
over square root 1 minus beta squared, right? So 1 minus beta squared is 1 over gamma. All right. So we can fix this if we simply maybe write and it will cancel out in the end. Right? So if we do not do this, because that's not a proper 4 vector, if we write the 4 velocity eta just essentially cancelling out this gamma here, gamma and then c and e, then it works out. But what this is, it's gamma dx over dt, right? And now you recall time dilation, right? If you have a particle moving with some velocity v, then the co-moving time g, or the proper time tau was t over gamma, right? So if you're looking at some particle moving with velocity v, well, remember that it experiences actually less time. So d tau is dt over gamma, right? That was the time dilation that we had derived. We have actually exactly that here, right? dt, we have this as dx over dt over gamma, right? So this is dx over d tau. So we take the derivative not with respect to our coordinate time here, which is pretty arbitrary, can be in the frame. If we take the time derivative with respect to the proper time of what is moving, and that is uniquely defined. There we have essentially the coordinate dependence cancelled out. And if we do that, then you'll figure out that c dot c is actually constant. And I think that's one of the homework problems of the neuroscience. I think that you must still be relying on that. A couple copies. So you will figure out in one of the homework problems what eta actually is. And now thinking about it, if we go ahead, we pretty much have to calculate that now. Because if we go on to defining momentum, we need that. So should we just do that? Maybe continue over here. So, remembering that eta was gamma c and velocity v, that means eta dot eta equals minus the zero component, so minus gamma squared c squared, and then plus gamma squared e squared. Let me take a minus c squared gamma squared out. Then we're left with 1 minus e squared over c squared. But again, 1 minus beta squared is 1 over gamma squared. So this